Hello everyone, welcome to RN Tutorials. Now we are going to discuss capillarity, which is one of the characteristics of a liquid under fluid mechanics and hydraulic machines. So what is capillarity? First I want to give the definition for the capillarity. So the capillarity is defined as a rise or fall of a liquid inside a glass tube when we insert it uh, in a liquid. So it is a rise or fall of the liquid in a glass tube whenever we insert in a liquid which is in a container. So again, this characteristic is due to the adhesive and cohesive properties of the fluid. So due to the adhesive and cohesive properties of the molecules of the liquid, we'll be facing the rise or fall of the liquid. So when we get the rise and when we get the fall means if a liquid is having maximum adhesive property, adhesive means sticking property of the fluid particles or fluidic molecules to any other external body. So in that condition, we'll be facing the rise of the fluid inside the glass tube, okay, over the external body. And similarly, if a liquid is having maximum cohesive property, so which will give the fall of a liquid, so in which we face the fall of the liquid inside the glass tube. So that means here due to the adhesive property, continuous molecular attraction and repulsion, even it is having continuous attraction and repulsion, if the adhesive property is more for the fluid particles, so due to that sticking of the fluid particles takes place to the external bodies. So due to that we will be getting the rise of the liquid in the glass tube. Similarly, if the fluid particles are having more cohesive property, so if the molecules are having more cohesive property, which means all the molecules will try to compact together, so the attractive forces will be more than the repulsive forces between the fluid molecules. So in that condition, uh, there will be no sticking property of the fluid particles to any other external body. So due to that, the fall of the liquid will be getting inside the glass tube whenever we insert into the liquid which is having the maximum cohesive property. So due to this adhesive and cohesive property of the molecules, will be facing the rise or fall of a liquid in a glass tube whenever we insert into a liquid. And similarly, I want to give small example. In a container I am taking a water. So in that water, I have inserted a glass tube. So whenever we insert a glass tube in a water, we'll be facing the rise of the liquid because water molecules used to have maximum adhesive property. So due to that adhesive property, all the molecules will try to raise over the external surface, sorry, over the internal surface of the tube. So the particles try to stick to the wall surface of the glass tube. So due to that, again the raise of the liquid takes place inside the glass tube. So whatever the height you are getting, that is called as capillary raise or capillary raise here. So the height obtained in the glass tube is the capillary raise, so which is obtained for water, which is the capillary raise. And similarly, in a container I want to take a mercury. So in that mercury, if you inside a glass tube, we will be facing the capillary fall. Why? Because here the mercury molecules used to have maximum cohesive property than the adhesive property. So due to that cohesive property, all the molecules always try to be together, compacted together due to the more molecular attraction. So in that case we can see the capillary fall inside a glass tube. Okay, whatever the height, that is the depression inside the glass tube is obtained, is called as capillary fall. So this is about the capillary raise and capillary fall, which is due to the maximum adhesive property, which is due to the maximum cohesive property, respectively. So now I want to give an expression for the capillary raise or fall. So whenever you consider raise or fall for any liquid, so according to the analysis, the same formula will be getting for raise or fall. So I want to take the water, that is the capillary raise, an example for deriving an expression for the raise or fall. So in a container, again I am taking a water. So when we insert the glass tube, we can face the raise. So whenever the raise is has taken place inside the glass tube, over the surface here, whatever the surface you are getting, that will be the curved surface. So due to the sticking property only, due to the adhesive property only, we'll be getting the curved surface in a glass tube. Okay, so on this curved surface, there is a surface tension takes place, which will be compensating the weight of the liquid which is present inside the glass tube up to a height of h. Okay, so here I can say that at the surface of the water in a glass tube, it will be having a surface tension. So surface tension means we can take the force due to surface tension. So how it will be acting means it will be acting in this direction. Why? Because surface tension means which is the force acting per unit length whenever the two dissimilar fluids come in contact with each other. So water is one fluid and the air which is above the surface is another fluid. So when these two are in contact, automatically the surface tension takes place over the surface of the liquid in the glass tube. So this direction is represented for the force acting in a particular direction, which is due to the surface tension. Okay, so this is the force due to surface tension. That force due to surface tension can be written as sigma into L, surface tension into length. Why? Because surface tension formula is force per length. So force is equal to sigma surface tension into length. And again here it is acting at a particular angle. Okay, with certain inclination it is acting. So I want to take the theta as an angle of contact between the force due to surface tension and the glass tube surface. Theta is an angle of contact, which is an angle between the surface of the glass tube and the direction of the force due to surface tension. So in this condition, again I have said that the weight will be acting, whatever the raise has taken place inside the glass tube. For that water it can have certain weight, so that weight I am assuming as W. Okay, this weight is applicable. I'm giving this weight to up to the height of H only, which as the raise has taken place. Okay, so here the constant level you are getting. So after inserting, the moment is given to the liquid due to the adhesive property, and at a particular position the level is becoming constant, means whatever the weight has taken place inside the glass tube will be compensated by another force. So that force is due to the surface tension only. So to analyze that, I want to divide this force due to surface tension into two components, horizontal and vertical. So the horizontal component is sigma into L into sine theta. Okay, and vertical component is sigma into L into cos theta. According to the rectangle division of the two rectangular components, we can write these two forces. Okay, vertical direction and horizontal direction. So here whatever the weight consisting for the water inside the glass tube up to the height of the H is equal to the force due to the surface tension which is acting in vertical direction. When these two becomes equal, the constant level will be getting, there is the equilibrium condition for the water which has raised inside the glass tube. So according to the equilibrium condition, we can say that whatever the weight of the liquid is present inside the glass tube up to the height of the H can be equal to the force due to surface tension in vertical direction. So I want to write the same sentence: weight of the fluid in the glass tube is equal to force due to surface tension in vertical direction. So first I want to write the weight of the fluid as W, and which is equal to force due to surface tension, which is sigma L into cos theta. Already we have written sigma into L into cos theta. So I want to modify the weight as in terms of the properties of the fluid. So we can write the specific weight. Already we know about the specific weight, which is already defined as weight acting per unit volume. So weight by volume is the specific weight. So in this condition, from this specific weight, we can write the W is equal to specific weight into volume. So again, specific weight can be written as, already we have discussed while discussing about the properties. So the specific weight again can be written as rho into g, density into gravitational acceleration, and the volume as it is. Okay, this is the modified form. And again, the volume can be modified in terms of the area of the glass tube in the height. So here volume we need to consider for the weight up to the height h we are considering. So volume can be written as area of the glass tube into height. So meter square into meter, again it will give you the volume. So the volume again can be written as area into height. Okay, this area into height up to this height, which will give you the volume of the liquid up to the height it has raised. Okay, so this I want to substitute here. So which is rho g into area into h is equal to sigma into L into, so in place of L again we can write pi into d. So L means what? On a particular length where the surface tension is taking place, that is the force acting per unit length. Here around the circumference of the glass tube, the sigma, that is the surface tension, will be acting. So circumference means which can be, we can consider as a length along which the surface tension is acting. Okay, that's why the length I have written as pi into the circumference. Okay, so I want to again modify the area. How can we write it? As area of the glass tube is pi d square by 4. Again write the equation as rho g into pi d square by 4 into h, which is again equal to sigma into pi d cos theta. So cancel the similar terms here, pi gets cancelled. Okay, and again the d 1d will be getting cancelled. Okay, so here d will be remaining. So finally, by keeping the h on left side and taking all the remaining terms to the right side, we'll be getting h is equal to 4 sigma cos theta. 4 comes here, 4 sigma cos theta by rho g, this remaining d. So 4 sigma cos theta by rho gd. So this is the equation we can derive for the capillary raise or capillary fall. Even you analyze the capillary fall, the same equation will be getting. So which is the final equation, final expression for the capillary raise or capillary fall? Okay, which is equal to 4 into surface tension cos theta by density into gravitational acceleration into diameter of the glass tube, the known diameter of the glass tube. Okay, so this is the way of understanding about the capillary raise or capillary fall. Please try to remember the equation, that is the force formula for sigma cos theta by rho gd, which is very important for your competitive examination, in which he tried to ask what is the capillary raise or capillary fall, what is the equation we can write. So please try to remember the equation. And I hope you understand my explanation. So if you still have any doubt, please feel free to give a comment to my video, and I'll try to clarify your doubts. And once again, thanks for watching my video, and please share my videos and ask your friends to subscribe to my channel. Thank you all.